Good afternoon, everyone. So today in this session, we'll be starting with the concept of equilibrium, and we'll be also discussing the different types of equilibrium, and then we'll be starting with the power, right? So, so any body is said to be in equilibrium if the net force acting on the body is equal to zero, right? The net force on a body is zero, then the body is said to be in equilibrium, right? And the position where the body acquires the net force equal to zero, right? That position we call as position of equilibrium, right? So at equilibrium, the net force on the body is equal to zero, right? We can write here. So at equilibrium position, the net force on the body is equal to zero, right? So F net is equal to zero at the equilibrium position. And the position where the net force is equal to zero, let's suppose at x is equal to x naught, force is equal to zero, right? At force is equal to zero. So this will be called as the position of equilibrium, right? Position of equilibrium. This is the position of equilibrium. Now we know that force in case of conservative forces, right? Net force acting on the particle, right? It can be written as F is equal to minus du by dx, right? Minus du by dx. So at equilibrium position, du upon dx, that's the first derivative of potential energy, right? With respect to position, that should be equal to zero at the equilibrium position, right? So du upon dx will be zero at equilibrium position. You can see here we have plot potential energy versus position, right? Potential energy versus position. So at we can see here the slope of potential energy and position graph is different at different positions, right? So there are many points here like point A, point B, right? Point D, point E, right? This is the point H, right? We can see here at the point B, if we draw a tangent at point B, it will be parallel to x-axis, right? Or we can say the slope of this tangent will be equal to zero, right? Slope of tangent here is equal to zero. Or we can say at this point at B, the first derivative of the potential energy with respect to the position is equal to zero. Or we can say at this point the force acting on the particle is equal to zero. Or we can say B is an equilibrium position, right? B is equilibrium position. B is an equilibrium position, right? Equilibrium point. And similarly, we can see at the point E, the slope is once again equal to zero, right? Slope is zero because tangent here will be parallel to x-axis, right? So slope is equal to zero. Or point E is also a position of equilibrium, right? Point E is also equilibrium point. So there are two equilibrium points in this curve. One is point P, another is point E. And at rest of the points, point A, point C, the curve has some slope, right? At C, the slope is negative. At A, slope is negative. At C, slope is positive, right? So we can see at different points, the slope of a curve is different, right? And slope is zero only at positions B and E, right? Now the question is that which position will be a stable position and which position will be the unstable position, right? So we can say there are two types of equilibrium. One is the stable equilibrium, another is the unstable equilibrium. It means that let's suppose if we place a ball here, right? If we place a ball here at position B, right? And if we displace this ball either towards right or towards the left, right? Either towards the right or towards the left. If the ball regains its original position, right? If the ball comes back towards its original position, right, then we can say that this point is actually a stable point, right? This point is actually a stable point, and position will be called as stable equilibrium position. Similarly, if at point E, if we place a ball at point E, and now if we displace this ball E either towards left or towards right, then you can see that this ball will actually fall down, right, on both the sides. It will not come back, right? It will not come back. It means that This position here was a equilibrium position, but not a stable equilibrium position, because the ball did not regain its original position, initial position back, right? So we can say point E is a point of unstable equilibrium, right? It's an unstable equilibrium. So point P is stable equilibrium, point E is unstable equilibrium. So for stable equilibrium, if we displace a ball, a particle, right? A particle comes back to its original position, right? That's the stable equilibrium. And for unstable equilibrium, the particle does not come back to its original position, right? So that's the point of unstable equilibrium, right? So the force at E is zero and the force at P is zero. So both B and E are stable. Both B and E are equilibrium points, but B is stable equilibrium and E is unstable equilibrium, right? So at stable equilibrium, the body always has a tendency to come back towards the equilibrium position because of the restoring force. That's why we call it as stable equilibrium. And for unstable equilibrium, the ball or the particle does not have a tendency to come back to its equilibrium position. That's the unstable equilibrium position, right? So let's uh, write the condition for the stable and stable and unstable equilibrium, right? For stable equilibrium condition, for stable equilibrium, O should be equal to zero. It means that F is equal to zero. That's du upon dx will be equal to zero, right? Du upon dx will be equal to zero. Or we can say at stable equilibrium position, potential energy of the particle at that position should be a minimum potential energy. Or we can say d square d square double derivative of potential energy with respect to position, d square upon dx square should be greater than zero. Or we can say u should be minimum, right? U should be minimum. So this is the condition for a stable equilibrium position, right? For a stable equilibrium position, that potential energy should be minimum and the net force should be equal to zero. And at that position, potential energy should be minimum. Or mathematically, we can say the second derivative of the potential energy with respect to its position should be positive, right? It should be positive. Then the point will be called as stable equilibrium point, right? So it should be positive. Similarly, for unstable position, right? For unstable equilibrium position, F net should be equal to zero, or we can say the slope of potential energy and position graph should be equal to zero at x is equal to x naught. And for the position to be unstable, right? The second derivative should have a point of maxima, right? It should have a point of maxima, or we can say second derivative should be less than zero, right? Second derivative should be less than zero. So this position will be called as unstable position, right? Unstable position or unstable equilibrium, right? Unstable equilibrium. Unstable equilibrium, right? Now you can see here, let's suppose at point B, right? At point B, if it displace a particle towards a point C, then at point C the slope is positive. If the slope is positive but the force will be negative, it means at point C the direction of the force will be along negative x. And similarly at point A, if we displace the particle towards the point A, now at point A the slope of the potential energy here will be equal to, it will be a negative slope, right? Then the force will be in the positive direction. It means that now at this point the force is along this direction, and at this point the force is along this direction. It means that this force will try to always oppose the position of the body, right? Or it will try to restore the original equilibrium position of this body, right? So this is how the stable equilibrium position, in case of stable position, the force acts on a body, right? Similarly, in case of unstable equilibrium, right, the force here we can see at point C, the slope is negative, the force is in the positive direction, right? And similarly at point C, the force slope is at point G, the slope is positive. At point C, the slope is once again positive. Or we can say the force is along the negative direction in both the cases. So there is no chance uh, of particle coming back to its stable equilibrium position, right? So that equilibrium position we call as unstable equilibrium position. So this is the mathematical condition. Find out whether the equilibrium position is a stable or unstable. For stable equilibrium position, we have the second derivative positive, and for unstable equilibrium position, we have second derivative as negative, or there is a point of maxima, and in case of stability, there is a point of minimum, right? Now talking about the neutral equilibrium, right? So neutral equilibrium is the point when we apply a when we displace a particle, right, either towards left or right from its equilibrium position. Then what happens is that there's no restoring force at all, right? There's no restoring force at all, or we can say that no force acts on it, so that the particle will come back to its equilibrium position. So that position we call as neutral equilibrium, or we can say at neutral equilibrium, force is zero, right? Force is zero, or we can say du upon dx is zero, and this force or this slope of the potential energy versus position is zero throughout, right? It's zero throughout. There is no force at all. There is no restoring force at all. So that position we call as neutral equilibrium, right? It means that, let's suppose uh, if we place a ball here on the horizontal surface, right? If we place a ball on the horizontal surface here, and if we displace this ball towards this right? So there will be no force. This ball will actually move along the horizontal direction with some speed, right? And there will be no force acting on it, or we can say the net force on this body will be zero, or this ball will move with a constant speed, right? Acceleration will be equal to zero. So we could say that this position was actually neutral equilibrium, right? Neutral equilibrium. Neutral equilibrium. So at neutral equilibrium, there is no force acting on the body throughout the motion, right? Throughout the motion. Now let's try to solve some of the questions related to stable equilibrium, right? And unstable equilibrium. So we have been given a question: a particle moves in a potential region given by u is equal to x square minus 2x plus 100, right? The potential has been given here, that's equal to u is equal to 2x square minus 2x plus 100, right? So this is the potential energy of particle in some region, right? What we have to find, where to find the equilibrium position, right? We can also find whether the position is a stable equilibrium position or unstable equilibrium position, right? Now, for equilibrium position, F should be equal to 0, or we can say du over dx should be equal to 0, right? Now, let's take the derivative of this potential energy, that's d upon dx of, right? That's 2x square minus 2x plus 100. That should be equal to 0, right? So taking the derivative, it should be 4x minus 2. That should be equal to 0, or we can say x should be equal to 2 upon 4. That will be equal to 0.5. So this is the position. This is the position at which the net force acting on the body is 0, right? So at x equal to 1 by 2, the net force acting on the body is 0, right? Now let's try to find out whether this position is a stable position or unstable position, right? For stable position, we have the condition that second derivative of the potential energy with respect to position should be equal to or should be positive, right? For the stable position. That is, d square u upon dx square should be greater than 0, right? It should be greater than 0. Let's try to find out. So taking the second derivative of this, the second derivative will be equal to d square u upon dx square, right? That's equal to 4, right? That's equal to 4. And you can see 4 is greater than 0. That's positive, right? Positive. So it means this equilibrium position is a stable equilibrium position, or we can say x naught equal to 1 by 2 is a stable equilibrium position, right? It's a stable equilibrium position. It's a stable equilibrium position, right? So there is only one equilibrium point, that's x equal to 1 by 2 at x equal to 1 by 2, and this equilibrium point is actually a stable equilibrium point, right? Now talking about the next point, next question. The next question is that if F is equal to force is now given, right? Initially the potential energy was given, now the force is given as F is equal to 2x square minus 3x minus 2. Now we have to find the position of stable equilibrium, right? And we will see whether the position, stable equilibrium position will be at some point, or unstable position will be there, right? Now let's for stable equilibrium position, for equilibrium, force should be equal to zero, right? Force should be equal to zero. So for force to be equal to zero, we have to find the solutions of x where the force will be equal to zero. So that will be minus b, that will be 3 plus minus under root of p square, right? That will be 9 minus 4ac, right? That will be plus 4 multiplied by 2 will be 8. 8 into 2 will be 16, right? 16, right? Upon 2a, right? That will be equal to 4. So there will be two positions, two solutions. That will be 3 plus minus 5 upon 4, right? So there will be two solutions. One solution will be equal to, that will be 8 upon 4, that's 2, right? Another solution will be minus 2 upon 4, right? Or that will be equal to minus 1 upon 2. So there will be two positions, right? One position is what we call as 2. Another position is x equal to minus half, right? Now let's try to see at which position the equilibrium is stable and at which position the equilibrium is unstable, right? For stable position, for stable and unstable position, we'll try to find out the second derivative, that's d square u upon dx square, right? So or we can write it as df upon dx, right? Df upon dx, right? Df upon dx. So second derivative of the force will be, it will be 4x minus 3, right? It will be 4x minus 3. That will be equal to 4x minus 3, right? Now for x not equal to 2, this value comes out to be equal to 4 into 2 will be 8 minus 3, right? That's equal to 5, right? That's equal to 0, greater than 0, or we can say it's positive, right? It's positive. So from here, we can conclude that x equal to 2 is a stable equilibrium position, right? It's a stable equilibrium point. It's a stable equilibrium point. Now, similarly for x equal to minus 1 by 2, right? X equal to minus 1 by 2. D square u upon dx square is equal to 4x minus 3, right? X equal to minus 1 by 2. That will be equal to minus uh, 4 upon 2 minus 3, right? That will be equal to minus 5, right? That's less than 0. So it means that the second derivative is negative here, or we can say it's a point of unstable equilibrium, right? Unstable equilibrium. Unstable equilibrium. So x equal to minus 2, it's a point of unstable equilibrium. So the first point, x is equal to 2, was a stable equilibrium point, and x is equal to minus 1 by 2 is a point of unstable equilibrium, right? So, so this is how we can find the stable equilibrium position and unstable equilibrium position using the second derivatives of potential energy, right? Now, talking about the conservation of mechanical energy, right? We know that energy can neither be created nor destroyed. Nor destroyed. It can only be converted into one form to another form, right? In the same manner, in the same manner, if we have a conservative forces, right? The mechanical energy is present in the form. Mechanical energy is the kinetic energy plus the potential energy, and we know in case of conservative forces, there's a concept of potential energy, right? There's a concept of potential energy, right? Kinetic energy can get converted into potential energy, and potential energy can get converted into kinetic energy. If there are no frictional forces or loss in energies, right, then this energy will be always conserved, right? This energy will be always conserved in the form of mechanical energy, right? Or we can say in case of conservative forces, the total mechanical energy is always conserved, right? If there are no other non-conservative forces, right? If there are conservative or non-conservative forces also present, then the total mechanical energy may not be conserved, right? In that case, so but purely for conservative forces, the total mechanical energy is always conserved, or we can say sum of potential energy plus kinetic energy is always a constant, right? It's always a constant. So we can say total energy, that's always a constant, that's equal to constant, right? And mechanical energy, we mean that it's the potential energy plus kinetic energy, that's kinetic energy plus potential energy, right? That is always a conserved quantity in case of conservative forces only, right? Conservative forces only. If the non-conservative forces are also present, right? Non-conservative forces are also present, then there will be a loss in energy, right? Energy will be dissipated in different forms. Then in that case, mechanical energy will not be conserved, right? Mechanical energy will not be conserved. Or we can say uh, kinetic energy at some point one plus potential energy at some point one, right? And the sum of kinetic energy at some another point two plus potential energy at point two, they will be always equal, right? They will be always equal, right? So this is the concept of the conservation of mechanical energy, right? The total energy of the system is always conserved, right? Total energy is always conserved, right? It may be present in different forms, but the total energy is always a conserved quantity, right? Now, let's try to apply this concept of conservation of mechanical energy here in this question. The question is a block of mass 4 kg is moving on a frictionless horizontal surface, right? So it clearly says that it's moving on a frictionless horizontal surface. So it means that we have removed the non-conservative forces here, right? With velocity 2 meter per second and come to rest after pressing a spring, right? If the force constant of the spring is 100 Newton per meter, then the compression in the spring will be, right? So the situation is like this. The situation is like this. Let's suppose this is the horizontal surface, right? This is the horizontal surface here, right? This is the horizontal surface. And on this horizontal surface, let's suppose there's a spring like this. There's a spring like this. There's the spring, right? Now, it's in relaxed position, right? It's in relaxed position, and there is a block of mass 4 kg, right? 4 kg block, right? It's moving horizontally with a speed of 2 meter per second, right? The speed of 2 meter per second. So it's a 4 kg block, right? It's a 4 kg block moving towards right with the speed of 4 meter per second, 2 meter per second, where the spring constant has the value 100 Newton per meter, right? Now, when the block will strike the spring, right, it will compress the spring to some compression X, right? And ultimately, what's going to happen? The block will come to at rest. Now, the only forces involved here are the conservative forces, right? We know that the force applied by the spring is a conservative force, right? So there will be a concept of potential energy, or we can say the kinetic energy lost by the block will be stored as the potential energy in the spring, right? Will be stored as the potential energy in the spring. It means that when the block stops, the total kinetic energy of the block will be transferred as the potential energy in the spring, right? Or we can say kinetic energy of block will be stored as potential energy in spring, right? And we know the potential energy stored in the spring is half kh square, where x is the compression, right? So initially the kinetic energy was half mv square. So this will be stored as the potential energy of the spring, that will be equal to half kh square, right? Or we can say mv square will be equal to kx square, right? Mv square will be equal to kx square, right? We have to find the compression, right? The mass is given as 4 kg and the speed is 2, that's 2 square, that's equal to 4. And the value of k is given as 100, right? It will be upon 100, that will be equal to x square, right? Or the value of x will be equal to 4 upon 10, right? It will be equal to 4 upon 10, that is equal to 2 upon 5, right? Let's suppose 2 upon 5 meter, right? This will be the compression, maximum compression, right? That will be equal to 0.4 meters compression for the spring. So the maximum compression of the spring is 0.4 meters, right? A ball of mass 2 kg is released from the tower of Pisa, right? The kinetic energy generated in it after falling through 10 meter will be, right? So whenever a ball falls by a height h, then the potential energy equivalent to that height h will be converted into the kinetic energy of that ball, right? Because we know that gravitational force is a conservative force, right? Kinetic energy will be converted into the potential energy, or the potential energy will get converted into the kinetic energy, so that the total sum of the mechanical energy is always conserved, right? So when the ball actually falls by a height of 10 meter or through 10 meters, the kinetic energy generated will be the kinetic energy equal to the amount of potential energy released. That's equal to the weight of this body, right, multiplied by the distance through which it falls, right? So the weight of this body is equal to uh, weight of this body is equal to m into g, right? That will be 2 into 10, right? And the height through which it falls is 10. So it's nothing, it's equal to 200 joules. So 200 joules of kinetic energy will be generated here, because this energy will be the same energy that's equal to the potential energy, that is, and that potential energy of 200 joules actually gets converted into the kinetic energy of this ball, right? So this is how mechanical energy conservation of mechanical energy plays its role in case of conservative forces, right? Some total of kinetic plus potential uh, is always conserved, right? Or we can say the total kinetic energy can be converted into potential energy, and potential energy can get converted into kinetic energy, right? So that's the concept of the conservation of the mechanical energy in case of conservative forces, right? Now let's talk about the power, right? Let's talk about the power. So power, it's defined as the rate of doing work, right? It's defined as the rate at which the work is done, right? It's defined as the rate at which the work is done, or we can say power is nothing. It's the rate of doing work, right? It's nothing. It's the rate of doing work. Power is defined as rate of doing work, or the rate at which the work has been done, right? Now, or we can write it as a rate at which the work is done. That's equal to P power. That's dW over dt, right? dW over dt. So this is the rate at which the work is done. Or we can say this power, we call it as instantaneous power, right? It's the instantaneous power. Instantaneous power, right? So instantaneous power is nothing. It's the power delivered at a particular instant, right? Now the question is average power, right? The average power is nothing. It's the total work done upon the total time, right? The average power is nothing. It's the total work done. Let's suppose delta W is the total work done, and delta T is the total time, right? That's the average power. Or we can write it as total work upon total time, right? Total work upon total time. So this is the average power, right? This is the average power. And the instantaneous power is the rate at which the work has been done, right? So that's dW over dt. Or we can write this instantaneous power here. That's P is equal to dW over dt, right? dW over dt. And we know that the work is actually F dot dr, right? F dot dr, right? So this dw will be actually F dot dr upon dt, right? Now this dr upon dt is nothing, it's the speed or velocity, right? So force dotted with velocity is the instantaneous power, right? Or instantaneous power can be defined as it's the dot product of the force and velocity vector, right? It's the dot product of force vector and velocity vector. That's the concept of instantaneous power, right? So F dot V is the instantaneous power, and total work upon total time is the average power, right? Average power, right? So if we plot work versus time, right, then the slope of work versus time, right, or the tangent of work versus time will give us the instantaneous power, right? So we can say dw over dt, right? It will give us p instantaneous, right? P instantaneous. That will be equal to tan of theta of that tangent at that point on this curve, right? So that will be equal to tangent of this curve, right? That will give us the instantaneous power, right? So now, if the plot is given between the power, right? If the plot is given between the power, right, and time, you can see here power versus time. So we can write power here as equal to dW over dt, right? This is our power. So dW over dt is the power. So if we integrate this power with respect to time, it will give us actually the total work done, right? It will give us the total work done. Integrating it on both sides, right? Integrating it on both sides, let's suppose between the time t1 and t2, right? So this is nothing. This actually represents the area under power time graph, right? Area under power time graph. This is nothing. This is the area under power time graph. And this is nothing. This is the work done, right? This is work done. So we can say area under power time graph represents actually the work done, right? So you can see here, this is the plot, right? If this is the area under this power time graph for the time tt, then the area of this portion of this curve under this curve, right, will actually represent the work done, right? This will represent the work done. So this will represent the work done. So if we have to calculate the work done and power versus time graph is given, then we will just calculate the area of this portion, right, to calculate the total work done, right? So this area will give us the work done, right? This will give us the work done. So this is the concept of the instantaneous power, right? Now let's try to solve some of the questions related to it. The first question is that a small motor is used to power a lift, right? That raise a load of bricks weighing 100 Newton to a height of 20 meter in 40 seconds, right? What is the minimum power motor needed, right? The question is that in a lift we're placing bricks of weight 800 Newton, and we want to lift these bricks to a height of 20 meters, but in 40 seconds only, right? Now, what is the minimum power motor needed, right? So minimum power motor needed. So we're not accelerating these bricks. Actually, we are moving these bricks with a constant speed or constant velocity, right? So the power needed will be, let's first calculate the total energy for the total work done, right? The total work done will be equal to W, right? That will be equal to the energy present in these bricks, right? So the energy present in these bricks will be the potential energy present in these bricks at a height of h, right? That will be equal to the weight of these bricks multiplied by the height h. So the weight of these bricks is nothing, it's 800 newtons, right? Multiplied by the height h, that's 20. So this will be the energy, right? Supplied, that's 8,000 joules, right? That is 8,000 joules. Now, this much of energy is supplied, and this energy is supplied in 40 seconds, right? This energy is supplied in 40 seconds, right? So we can just write it at 8,000. Power will be 8,000 upon 40, right? It will be 200 watts, right? It will be 200 watts, right? It will be 200 watts, correct? So it will be a 200 watts of power supplied by this small motor to lift these bricks to a height 20 meter, right? In 40 seconds. So total energy. So here the instantaneous power will be 200 watts and the average power will also be 200 watts because we are slowly and steadily. It's not accelerating. It's going with a constant speed. So here in this case, it will be a it will be an average power, or we can say instantaneous power will be here equal to average power, right? That will be equal to 200 watts. Now let's move to the another question, right? The question is that the force required to tow a boat at constant velocity is proportional to the speed, right? If a speed of 4 kilometer per hour requires 7.5 kilowatts, how much power does a speed of 12 kilometer per hour require, right? Now the question is, it's a very interesting question, right? The question says that we're towing a boat, right? The force required to tow a boat at constant velocity is proportional to the speed, right? So let's suppose force is proportional to the speed v, or we can write force is equal to alpha v, replacing with proportionality with constant, right? So force will be equal to alpha times v. Here v is the speed, right? If this is the force, right, then v is the speed, instantaneous speed, right? And we are applying the force along the direction of the speed, or we can say that the instantaneous power will be equal to f dot v, right? That will be equal to f dot v, or that will be equal to alpha v to v square alpha v square, right? Or the power supplied to this boat will be proportional to v square, right? It will be proportional to the v square, right? Another question is that if a speed of 4 kilometer requires 7.5 kilowatt, how much power does a speed of 12 kilometer per hour require, right? Or we can say that P2 upon P1 will be equal to V2 upon V1 whole square, right? V2 upon V1 whole square, right? So this will be the condition, right? So P2 we have to find, right? That will be equal to V2 upon V1 whole square, right? Multiplied by P1, right? Now the value of V2 is 12 and the value of V1 is 4, and that will be whole square, and value of P1 is 7.5 kilowatts, right? 7.5. So it will be 3, right? 3 square is 9. So it will be 9 multiplied by 7.5, right? So it will be equal to 63 plus 4.5, right? It will be 67.5 kilowatts, right? So this much of power will be required, right? This much of power will be required uh, to move this boat with a speed of 12 kilometer per hour, right? So the power required for 7.5 kilometer was per hour, for power required for the 4 kilometer per hour speed was 7.5 kilowatts, and the power required for the 12 kilometer per hour will be 67.5 kilowatts, right? So this much of power will be required for this boat to move with a speed of 12 kilometers per hour, right? So this was the last topic of this chapter, right? This was the work energy power, right? We are done with the power, right? We are done with all the concepts of work energy and power. Now we are left with the circular motion, right? Circular motion, and then we'll be starting with the rotational motion or the system of particles as well. That will be started in the next lecture, right? So we'll stop here. See you in the next class.